Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is the AC voltage divider rule. Our objective is to learn to apply the AC voltage divider rule to quickly and directly solve for voltage across individual elements in series AC circuits. Bottom line up front, the AC voltage divider rule is the DC voltage divider rule using phasors. I cannot make it much simpler than that. This lecture therefore operates under the presumption the viewer is intimately familiar with the DC voltage divider rule from way back in the Basic Electronics 1 DC Circuit Analysis playlist, available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. Additionally, it is presumed the viewer has an understanding of basic series AC circuit properties. In our previous lecture on series AC circuits, we learned current through elements in a series circuit is the same when the sum of voltage rises equals the summation of voltage drops for any closed loop. These are the most fundamental properties of series AC circuits. If you recall, the DC voltage divider rule was a simple proportionality equation that allowed a user to quickly and directly solve for voltage across an individual element of interest without having to solve for total impedance and current values. Likewise for the AC voltage divider rule. The AC voltage divider rule states that the voltage across the element of interest, Vx, is equal to the impedance of the element of interest, Zx, divided by the impedance for that series path, Z single prime, times the voltage across that path, V single prime. Note that the ratio of Zx over Z single prime must be calculated first, and then one would multiply the resultant proportion times the voltage across that path. As an illustrated example of the AC voltage divider rule, consider the following series AC circuit comprised of two elements. The first element is a 300 ohm resistor, and the second element is a 12 microfarad capacitor. The source has an effective value of 120 volts and an excitation frequency of 60 Hz. Let's say we're being asked to solve for the voltage drop across each element. Note we are not being asked to solve for current, nor are we being asked to solve for total impedance. Educational and entertaining as these properties may be, they are merely diversions delaying us from reaching our intended goal. Let's see if we can use the AC voltage divider rule to quickly and directly solve for the voltage across each element. The complex impedance of the 300 ohm resistor is 300 ohms at an angle of 0 degrees. Let's call this impedance Z1. The complex impedance of the 12 microfarad capacitor at an excitation frequency of 60 Hz would be 221 ohms at an angle of -90 degrees. Let's call this impedance Z2. The AC voltage divider rule, solving for V1, suggests that V1 equals Z1 divided by Z1 plus Z2 times our source voltage E. Substituting in our given values yields V1 to be 96.6 volts at an angle of 36.4 degrees. Similarly, the AC voltage divider rule, solving for V2, suggests that V2 equals Z2 divided by Z1 plus Z2 times our source voltage E. Substituting in our given values yields V2 to be 71.2 volts at an angle of -53.6 degrees. There you have it. Two quick applications of the AC voltage divider rule yielded our desired results without any delay, toil, or tears. Given we save so much time using the AC voltage divider rule, we've got ample opportunities to check our work. There's two principal means of doing so, one via Kirchhoff's voltage law and the other one via Ohm's law. A Kirchhoff's voltage law analysis of this series circuit suggests that E equals V1 plus V2. The sum of voltage rises equals the sum of voltage drops. Given we solve for the voltage drops across individual elements using the AC voltage divider rule, we could substitute the results of one of our calculations to verify our second value. Let's do so for V2. An algebraic rearrangement of the Kirchhoff's voltage law equation for this series circuit solving for V2 suggests that E minus V1 equals V2. Substituting our given value for source voltage and our calculated value for V1 yields V2 to be 71.2 volts at an angle of -53.6 degrees, confirming our earlier calculations with the AC voltage divider rule. Additionally, one can also use Ohm's law to verify the results obtained using the AC voltage divider rule. Because these two elements are in series with one another, they should experience the same current. Source current Is equals I1, which equals I2. Ohm's law, solving for current, demonstrates impedance Z1 experiences 322 milliamperes at an angle of 36.4 degrees. Similarly, Ohm's law, solving for current, demonstrates that impedance Z2 also experiences 322 milliamperes at an angle of 36.4 degrees. Current through these elements is in fact equal. This is to be expected given they are in series with one another. Alright, let's try another illustrated example of the AC voltage divider rule, this time featuring a series combination of three elements. In an effort to make this lecture compact, note I've already taken the liberty of calculating the impedance for each element. The First element, Z1, has an impedance of 150 ohms at an angle of 0 degrees. Most likely this is a purely resistive element. The second element, Z2, has an impedance of 86 ohms at an angle of 85 degrees. Most likely this is an inductive element that features a tiny amount of internal resistance. Finally, the third element, Z3, has an impedance of 60 ohms at an angle of negative 90 degrees. Most likely this is a purely capacitive element. The source has a value of 80 volts at an angle of 0 degrees. We're being asked to solve for the voltage drop across each element using the AC voltage divider rule. Again, note we are not being asked to solve for current, nor are we being asked to solve for total impedance. Our only mission is to swing the AC voltage divider rule over our head, charge into the jungle, and come back carrying 3 voltage values slung over our shoulder as quickly as possible. Note the general use AC voltage divider rule formula doesn't change, despite the addition of more elements in series. The general use AC voltage divider rule formula states that the voltage across the element of interest, Vx, is equal to the impedance of the element of interest, Zx, divided by the impedance for that series path, Z single prime, times the voltage across that path, V single prime. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results.